purpose of this video is to introduce the idea of iterated integrals over non-rectangular regions, regions that are not rectangles. So let's consider a simple case of when we do have a rectangle in the xy plane. Let's suppose that we label that rectangle R, and it has endpoints A and B along the x-axis and C and D along the y-axis. Then we know that we can write the volume integral a couple ways. One way is to integrate with respect to y first. So we have the integral of f of xy from y equals c to y equals d. And then we take that result and we integrate it from x equals a to x equals b. Of course, we could switch the order of integration so that we integrate with respect to x first and then y, the integral from x equals a to x equals b, f of xy dx. We would then compute that and integrate the result from y equals c to y equals d. But what if the region R is not a rectangle, but maybe it's something like a triangle? And so for the next few minutes, we'll look at a situation where we have a triangle bounded by y equals 0, x equals 1, and y equals 2x. We want to know how to compute the volume integral in this case. So the picture is going to look like this. Here we have x equals 1. Here we have the line y equals 2x, and then the y-axis. So we're looking for the integral, what it means to integrate a function over a non-rectangular region like this. We're looking at this triangle, not this over here, but this triangle. So let's discuss the general strategy. We're still going to write a double integral, but we're going to do things a little bit differently. Up until this point, the endpoints for both the inside and the outside integrals have been numbers. But in this case, it's going to be different. The outside integral will always have numbers, but the endpoints for the inside integral will depend upon the outside variable of integration. So y equals something to y equals something, and that something has to be in terms of x. That's if we integrate with respect to x last. Or maybe we'll try to integrate with respect to x first. So now our endpoints would be y equals some number c to y equals some number d, and x now is going to vary between two values, where those two values depend upon y. So the big idea is that the outer endpoints are going to be numbers, but the inner endpoints, the things we're going to put in these boxes, are actually functions. So here's an outline of the process. First, decide whether you want x or y to be the outside variable of integration. Okay, now we're going to look at a particular example. We're going to try it both ways. And for our example, the method, whichever method we use, it's going to be comparable difficulty each way. But there are situations where one order of integration is easier than the other. We won't get to that in this video. Okay, so we're going to integrate with respect to x last. It's going to be the outside variable of integration. What we want to do at that point is we want to look at our region R and determine its smallest and largest values. So in our case, if we integrate with respect to x last, we can see that over this triangle, the smallest value of x is 0 and the largest value of x is 1. Those are going to become then the outside limits of integration. X is going to go from 0 to 1. Now we have to determine the limits of integration for the inside integral. Now here's the way to do that. Suppose you just choose an arbitrary value of x between 0 and 1 and draw a vertical segment at that value and determine the smallest and largest values of y, which will depend upon x. So what I've done here is I've just moved some distance along the x-axis where x is between 0 and 1, and I've drawn a vertical segment there. Now I'm going to ask myself, along this vertical segment, what are the smallest and largest possible values of y? Well, the smallest value of y, regardless of where I choose my value of x, the smallest value of y will always be 0. Now the largest value is always going to be up on the line where y is equal to 2x. So let's say that again. For our example, the smallest value of y is 0, and the largest value of y is on the line y equals 2x. So they become the inside limits of integration, y equals 0 to y equals 2x. So what we will do is we will evaluate this inside integral and then take the result and integrate it with respect to x. So we're going to look at a particular example. We're going to look at the case where f of x is x plus y. So the first thing, I'm going to take the inside integral and I'm going to just work with it. So I'm going to take what we have here and I'm going to put it down here. So y is going to vary from 0 to 2x, and I have x plus y. Now we're going to integrate or anti-differentiate with respect to y, which means we treat x as a constant, like a 3 or something like that. So the antiderivative of a constant with respect to y would be just that constant times y. So that gives us an xy here. If we anti-differentiate y with respect to y, we get y squared over 2. Now what we will do is we will substitute our endpoints 0 and 2x into this resulting expression. Now, if we substitute 2x in for y, we'll have x times 2x. And if we substitute that in here, we'll have 2x quantity squared, all divided by 2. When we substitute y equals 0 into this, we get just 0. So this simplifies to be just 4x squared. So that is the value of just the inside integral. So now we have to take that result and we have to integrate it from x equals 0 to x equals 1. And that's fairly straightforward. The integral from x equals 0 to x equals 1, 4x squared. The antiderivative is 4/3 x to the third. Substitute 0 and 1 in, and we get 4/3. So that's our final answer. Now what we're going to do is we're going to do the integration in the opposite order. But before we do that, let me just keep some things in mind. The limits of integration on the outside integral are always numbers and never contain variables. The result of the first integration is usually an expression, and the result of the second integration has to be a number. It can't have a variable left. So you notice how we got a number here and nothing containing a variable. Now suppose we had chosen y as the outside variable of integration. Now in our situation, y is going to vary between 0 and 2. We can see that from our diagram. So that's going to say that our values of y will vary between 0 and 2, and they become the limits of integration for the outside integral. What we have to do is we have to determine the smallest and largest values of x for each value of y. So now we're just going to choose an arbitrary value of y between 0 and 2, and we're going to draw a horizontal segment at that value of y and determine the smallest and largest values of x, and we will substitute those in here and there. So let's take a look. What I've done is I've moved up some arbitrary distance y, and I've drawn a horizontal segment. And what I want to do is I want to figure out the x values at the beginning and at the end of this endpoint. So I want to find the x value there and the x value there. Well, regardless of where I draw my horizontal segment, the x value here is going to be x equals 1. Now the x value on the left-hand endpoint is going to depend upon y somehow. Well, how does x depend upon y? If we look at this equation, y is equal to 2x. So that says that this left-hand endpoint will be y over 2. So my left-hand endpoint is always going to be y over 2. My right-hand endpoint will be x over 1. So to say that again, in our example, the largest value of x is x equals 1, and the smallest value is on the line y equals 2x. So we solved y equals 2x for x. We got x equals y over 2. So now our inside integral, just the inside integral, becomes the integral from x equals y over 2 to x equals 1, x plus y dx. If we integrate this with respect to x, the antiderivative of x is x squared over 2. If we integrate y with respect to x, we're treating y as a constant, so this will just be yx. Now we will substitute the endpoints 1 and 0, 1 and y over 2 in for x. It's a little bit more tedious in this example. If x is 1, we'll have 1/2 plus y times 1. If x is y over 2, this will become y over 2 quantity squared divided by 2 plus y times x, which is y over 2. Now, if you do some algebra and simplify this a little bit, you'll get 1/2 plus y minus y squared over 8 plus y squared over 2, which simplifies fairly nicely to be just that. Now, this was the result of our inside integral, where we integrated with respect to x. Now we're going to take this result and we're going to integrate it with respect to y, where y varies over the smallest and largest values. And from before, we know that y varies from 0 to 2. So we're going to take this result and integrate it with respect to y. Now I'm going to leave out a few of the details. There's a little bit of algebra that's involved. You have to be careful about your subtracting and your fractions, but the final answer is in fact 4/3. Let's take a look at a slightly different example. One of the challenges of doing problems like this is choosing the endpoints. So we're going to suppose that y is the region bounded by, that r is the region bounded by y equals 0, x equals 2, and y equals x squared. So that looks something like this. Y equals 0, x equals 2, y equals x squared. Now we're going to practice just setting up the limits of integration, doing it both ways, integrating with respect to y first and then x, or perhaps integrating with respect to x and then y. So let's do the first way. Now we work our way from the outside in. We first look at our picture and ask ourselves, what's the smallest and the largest value of x? We're looking at this region right here. The smallest value of x is 0 and the largest value of x is 2. So that says x is going to vary from 0 up to 2. Once we've done that, we choose an arbitrary value of x between 0 and 2 and we draw a vertical segment here. And that's what I've done. And we ask ourselves, for this vertical segment, what's the smallest value of y? What's the largest value of y going to be? Well, the smallest value of y is always going to be y equals 0. The largest value of y is going to be on the parabola where y is equal to x squared. That's right here. So that's going to be my upper endpoint. Y equals x squared. So my outer endpoints are just numbers, and my inner endpoints depend upon the outside variable of integration, which is with respect to x. Now suppose we switch the order of integration. So now we integrate with respect to x and then with respect to y. Because y is the outside variable of integration, we're going to focus on it first. We're going to take our picture. We're going to ask ourselves the smallest and largest values of y. Well, we're looking at this region here. When x is 2, y is 4. So the smallest value of y is going to be 0, and the largest value of y is going to be up here when y is equal to 4. Now we have to determine the inside endpoints. We're going to pick an arbitrary value of y between 0 and 4, and we're going to draw a horizontal segment. And what we want to do is we want to determine the left-hand endpoint and the right-hand endpoint of the segment, but we want to determine them in terms of x. Well, regardless of where I draw that segment, the x value, the largest x value, is going to be 1. The left-hand endpoint is going to depend upon the point on the curve. It depends upon what y is. If y was down here, x would be pretty large. Up here, this endpoint is pretty, let me say that again. If I had drawn my horizontal segment down here, x would be smaller than it is up here. We know that y is equal to x squared. If we solve that, we can get x in terms of y. X is equal to plus or minus the square root of y. Well, x has to be positive, so we're going to just look at the square root of y. Now notice how if y is 0, x is 0. If I had drawn the segment down here, y would be 0, x would be 0. If y is all the way up here at 4, we know that x has to be 2, which it is right there. So my lower endpoint is going to be the square root of y, x is the square root of y, and my upper endpoint is going to be x. My lower endpoint is going to be x equals the square root of y. Here's some problems for you to do in preparation for class. Evaluate the volume integral x squared y, where r is the region bounded by x equals 1, y equals 0, and y equals the square root of x. That's this region. So it's everything in here, everything in there. Secondly, suppose that R is the region bounded by x equals 0, y equals x to the third, and y equals 8. That's going to look something like this. So this is y equals x to the third. We want the region bounded by that curve, y equals 8, and x equals 0. See if you can fill in the endpoints. You're not computing an integral of any sorts. I would just like for you to fill in the endpoints correctly. Now here's a word of warning. If you don't put your endpoints in correctly, instead of generating endpoints that give you this region, you might accidentally be generating this region. So that's something that you want to check for. See you in class.